Good afternoon, everyone, and welcome to today's AMPC webinar around water recycling. Obviously, it's a very hot at the moment, and we've got a really good number of registrations on the line. This webinar is recorded, so if you wish to share it later or part of it, please feel free. We'll send out the link afterwards, and happy for you to share it around. So I'll introduce Megan, who is our Program Manager for Sustainability at AMPC, and he's going to introduce the presenters. During the webinar, if you've got any questions, we really encourage you to use the toolbox, type your question in, and then Matt will, at the appropriate time, ask the relevant presenters. Over to you, Matt.
Thanks, Amanda. Today we've got two speakers talking about recycling opportunities and water recycling opportunities and next steps for processes. Our first speaker is Dr. Han Tung from the University of New South Wales, who has just completed a report on water recycling opportunities inside red meat processing. And then the second speakers will be Max Barnes and Gareth Forde, who will be talking about next steps and a pilot for low cost water recycling. So our first speaker is Dr. Han Tung, so I'll hand over to Han.
Thanks, Matt. Hey everybody, I'm Han from UNSW, and I'm presenting some of the findings and outcomes from our project, which looked at the technical and economic feasibility of water recycling in red meat processing abattoirs. The Australian red meat processing industry uses large quantities of water to maintain high levels of sanitation. Potable water is used throughout the various stages of meat processing, ranging from washdown of stockyard all the way to rinsing of final meat products. And due to this, in times of drought, meat processors are often perceived as overusers of water, increasing potable water costs and thereby increasing tensions between red meat processors and the local community for consumption of potable water. Therefore, the aims of this project is to provide red meat processors with recommendations to reduce potable water consumption via the identification of waste streams suitable for recycling or reuse, as well as assessing its technical, environmental, and economic feasibility. The project was broken down into 4 milestones. Milestone 1 was first to collect abattoir operational data to establish the current volume of potable water consumed as well as its costs. This was achieved by a survey sent out to participating processors, as well as site visits and interviews. Milestone 2 was then to identify the quantity and quality of the abattoir waste streams before selecting streams that were most suitable for reuse or recovery. Milestone 3 then looked at pairing the selected waste streams with proposed treatment trains to assess their technical feasibility through microbial risk assessments, biowind and wave RO modeling. Milestone 4, which is the last milestone, was then to assess the economic and environmental feasibility, and that was achieved through a comparative life cycle assessment as well as net present value ROI assessments. As previously mentioned, Milestone 1 looked at data collection. As mentioned before, we went through a survey as well as site visits and interviews. Through the site surveys, we collected operational data such as potable water consumed on site, together with economic information such as trade waste and potable water costs. Visits and interviews with abattoir personnel were also used to collect process flow diagrams, piping instrumented diagrams, and site-specific information. Findings from Milestone 1 kind of showed us that cattle processors utilize an average of 8.94 kiloliters per ton of hot standard carcass weight of potable water. Sheep processors use slightly less at 6.55 kiloliters. And looking at the trend over the years, potable water consumption has been, reduced throughout the last 20 years, with a significant reduction of 14% since 2005. However, at 8.94 kiloliters per ton of hot standard carcass weight, shows us that there's still a need to further improve by reducing further reducing potable water consumption.
Excuse me, Hans,
Yep.
sorry, can I maybe ask you to, it's just some of the people can't actually see your presentation at the moment, so maybe if
Okay.
you stop sharing your screen and we'll reshare it and see if that helps.
Give me a
I
second.
can see it, but others can't.
I'm just gonna stop.
And we'll make you the presenter again. Let's see if that's better. You just need to.
I'm not a presenter yet. Yep. And I'll do it.
Can someone just write in the comments whether they can actually see the presentation now, if that's better?
Is that good for everybody?
Looks like it's better for most people. Sorry about that. Yeah, continue on.
Okay.
Sorry.
No, that's all good. So some of the findings from Milestone 1, we looked at obviously the potable water and wastewater disposal costs. Cost of potable water, as you can see here, there's a large variation. It ranged from anywhere between $1.46 all the way up to $4.50 per kiloliter, and that was largely due to the processor's geographical location, which determines their accessibility and availability of water. As for wastewater disposal, currently wastewater is being handled via two ways, either trade waste disposal or via irrigation post on-site treatment. Therefore, the trade waste costs also varied largely from anywhere from 25 cents per kiloliter all the way up to $2.54 per kiloliter. And that's highly dependent on the volume and the quality of the wastewater being disposed. On average, the processes that we surveyed discharge an average of 7.23 kiloliters of wastewater, and that can result in a significant yearly operational cost due to trade waste. Also, from the interviews with the participating processors, it was clear that there were growing concerns regarding the increasing cost of potable water due to decreasing water availability. This highlights the need for us to explore water reuse and recycling options, where every percent water saved actually counts significantly. Recovering 1% of water will save approximately 9,600 kiloliters a year, which amounts to 28,000 at the current potable price of $2.98. However, from our interviews as well, we noticed that there's a massive barrier to the adoption of water recycling and reuse, and that was due to the inconsistencies in the current legislation, resulting in a perception that the processors' export market access would be affected should they choose to use recycled water in their abattoirs. And that's most probably the reason why the industry is reluctant and hesitant to consider water recycling or even reuse. So based on we actually reviewed the relevant legislations. So we looked at all the relevant legislations. They've got AS 4696, which is the Food Standards, Meat Notice 2008, the MICOR from Department of Agriculture, as well as Codex. And there was actually there's no evidence that recycled water is prohibited in meat processing as long as they comply with the Australian Drinking Water Guidelines. So this further highlights the possibility for processors to consider water recycling to increase their water savings and improve their water stewardship. Findings from this project can also act as a proof of concept that water recycling is technically feasible as long as they stay compliant with the relevant legislation. Moving on to Milestone 2. Milestone 2's aims were to quantify the volume of wastewater produced by each abattoir process, establish the water quality of those waste streams, as well as select waste streams that were most feasible for reuse or recycling. As you can see from this process flow diagram that there are many different waste streams generated from an abattoir process. And we did face a few limitations and challenges, one of which is that abattoirs do not properly meter their water, do not basically meter their processes. So it's difficult to actually collect water quality data as well as flow data. Wastewater generated from individual processes were not segregated. Often they were basically commingled and sent down the same drain. And as such, they only monitored limited water quality parameters, and most of it only focused on the treated effluent for their trade waste and disposal compliance. So as part of Milestone 2, we basically had to review the data that we collected from Milestone 1 and basically look at the existing literature as well as previous studies to ascertain, to basically fill up the gaps before we can start in step 2 to rank the waste streams based on their volume and their water quality. We obviously wanted to focus on streams that were high in volume and low in contamination because those are the easiest to treat and probably has the most benefit for, it's most opportunity for reuse and recycling. So just very quickly, we basically ranked all the waste streams and from all the different processes in an abattoir, and ranking of the waste streams identified the kill floor to be the largest producer of wastewater, contributing to 27% of the total wastewater produced, followed by the stockyard wash and combined stick waters. However, of these three mentioned here, only the kill floor waste stream was deemed suitable due to its contaminant strength. And that's what we actually developed a ranking system to basically start to score each individual stream based on its volume and its strength. As such, from the scoring system that we developed, we basically ranked and we found that the top 4 streams most feasible for reuse or recycling were the boning room, site chiller wash, kill floor, and boiler wash waters. The full ranking and more details can be found in the AMPC report too. So with the selected, with the waste streams selected from Milestone 2, Milestone 3 was then to now propose and select 3 water reuse or recycling options. The 3 options that we proposed were option 1, direct reuse with minimal treatment. Option 2 was to recycle to a non-portable Class A standard. And option 3 was to recycle to potable water standards. And these options were then subsequently evaluated based on a qualitative microbial risk assessment to establish the log removal values required for the treatment, as well as a multi-criteria assessment to select the best treatment train for each option. 2 modeling softwares were used as well. BioWin and DuPont Wave softwares were used to help determine the removal efficiencies of the treatment processes. So option 1, direct reuse, looked at reusing wastewaters generated from the boning room, site chiller, and the boiler wash directly as stockyard washdown water. Given the low amount of contamination in these streams, the process only required a screen for removal of large solid contaminants, followed by chlorination to achieve the minimum 2 log removal values for E. coli. And this option could yield savings of about 204 kiloliters per day, which is about 8% of the abattoir's daily usage. However, this has limited use as it can only be used as washdown water in the stockyard. So it does not necessarily and cannot be used anywhere else. Option 2 was to treat the kill floor wastewater to a Class A non-portable standard. And this was achieved through a membrane bioreactor and chlorination as the final disinfection step. So just briefly, a membrane bioreactor essentially conventionally activated sludge is used for nutrient removal, followed by a solid liquid separation step by acetylene. An MBR, on the other hand, which is what we propose to use, essentially combines the conventional activated sludge and settling process into one using ultrafiltration membranes as well. And this not only reduces the process's overall footprint, but also improves the pathogen removal efficiency, allowing the treatment train to achieve the required LRVs for non-potable Class A water production. It should be noted that whilst MBRs are more compact and efficient, they are also susceptible to oil and grease. Therefore, proper water quality sampling will be needed prior to adoption of this technology. And a potential way to solve this issue was to have a save oil tank used upstream of this treatment process for flow balancing as well as removal of oil and grease. For option 2, we used biowind modeling to pretty much simulate a membrane bioreactor to establish its removal efficiencies. And the modeling results demonstrated that an NMBR was capable of producing non-potable Class A water. As you can see from the Class A, basically the MBR effluent was, achieved the Class A standards. In fact, surpassed the Class A standards for BOD, total suspended solids, nitrogen, and phosphorus. This treatment train was capable of producing 719 meters cubed a day of Class A water that succinctly met the abattoir's non-potable needs. Although this option can yield significant water savings, again, it's limited to processes that utilize Class A water, which tends to be washed down waters as well as in other plant amenities. Therefore, it does not have as much utility compared to potable water. Option 3 was to recycle all the selected waste streams to potable water standards. Again, that involved the use of an MBR for nutrient and pathogen removal, followed by an RO membrane for dissolved solids removal. The RO unit also provides an additional barrier to pathogens, enabling the treatment train to surpass the minimum required LRV for drinking water. This is also part of a multi-barrier approach, which is required by the Australian Drinking Water Guidelines, with chlorination also used as the final disinfection step. Again, we use biowind modeling to basically show that the nutrient removals were achieved, and the WAVE RO modeling software was used to design and size a RO system. The modeling results showed that to achieve a recovery of 88%, a two-stage RO system with concentrated recirculation was required, and that was able to produce 1,023 meters cubed a day of potable water, which accounts for up to close to 32% of an abattoir's daily potable water requirements. And given that potable water can be used in a wide range of abattoir processes, recycling wastewater to potable standards would allow processes to achieve the most significant water savings. So with the waste streams, with recycling waste streams to potable standards being the best option to achieve significant water savings, a comparative LCA was conducted to evaluate the environmental impacts attributed to the adoption of potable water recycling. Subsequently, an economic feasibility assessment was conducted to assess the economic viability of the water recycling options, where a net present value over a 15-year time period with an ROI projection advising on the capital payback period. A sensitivity analysis was also conducted to look at the impact of potable water prices on the projected NPVs and ROIs. So as part of for milestone 4, we looked at 3 different scenarios. Scenario 1 being the base case where no recycling is considered. Scenario 2 was the case where internal recycling was adopted. Internal recycling involves treating the selected waste streams via the proposed MBR and RO unit to produce potable water. While scenario 3 was the case where end-of-pipe recycling was considered. End-of-pipe recycling differs to internal recycling, with the abattoir's wastewaters first treated by the local utilities wastewater treatment plant for nutrient removal, followed by an additional ultrafiltration and RO membrane used to treat the water to potable standards and recycle. Just very briefly, the comparative LCA assessed each scenario across 10 different environmental impact indicators. a decrease in impact score indicates an environmental benefit, while a decrease in impact score indicates an environmental benefit, while an increase in impact score indicates an environmental burden. Changes in impact scores that exceeded 10% were deemed to be significant, with anything less than 10 considered insignificant and not considered in the study. Internal recycling showed, so based on our results, internal recycling showed that there were significant changes in 6 impact indicators, while end of pipe resulted in 4 significant changes. Regardless someone's phone's going off. Regardless of recycling configuration, recycling of waters generated an environmental benefit for 2 impact indicators of mineral resource scarcity and freshwater consumption, which was obvious due to the reduction in water extracted from the environment and the subsequent impact. However, internal recycling did contribute to more of an environmental burden due to the increased energy consumption and sludge production associated with the use of the MBR for nutrient removal. The end of pipe, on the other hand, did not have that because it relied on the conventional wastewater treatment plant run by the local utility for nutrient removal. Moving on to the economic feasibility, the total capital investment costs for both internal and end of pipe recycling were estimated based on CapEx values obtained from wastewater treatment case studies. Working capital was assumed to be 15% of the fixed capital investment. And as such, the total CapEx for internal recycling was estimated to be close to $3 million, while end of pipe recycling was found to be around 1.7 million. This shows that internal recycling was more capital intensive as it required a dedicated MBR for nutrient removal. However, this translated to a reduction in operational expenditure due to lower trade waste disposal volume. As you can see here, when it comes to operational expenditure, internal recycling had a lower OPEX of around 400,000 a year compared to end of pipes 820,000 a year. Again, that was due to the fact that internal recycling was not reliant on the utility's conventional wastewater treatment plant, and hence we're paying less for trade waste treatment. As part of the net present value and ROI projections, the financial savings from the reduced volume of potable water purchased from the utility was considered as a revenue stream, and that amounted to close to $1 million a year at the current potable water price of $2.98 a kiloliter. So from the survey data, it was clear that potable prices could range from as low as $1.45 all the way to as high as $4.50. As such, a sensitivity analysis was developed to look at the effect of potable water price on MPVs and ROI of the 2 options. Sensitivity analysis showed that at a current average price of $2.98, internal recycling was more feasible than end of pipe recycling, achieving a capital recovery after 8 years at an ROI rate of 10.2%. The end of pipe recycling scenario did not achieve capital recovery after its 15-year lifespan. However, when the potable prices are high at $4.50, both options were economically feasible, achieving a capital recovery after 5 years and ROIs of 23% each. And as expected, when the prices were low at $1.45, both recycling options were not economically feasible. So in conclusion, the project has proposed 3 options with recycling to potable water having the greatest utility, thus allowing the processes to make the most of water savings. However, there are a few issues that need to be addressed prior to the adoption of potable water recycling. First is that abattoirs need to have proper water metering as well as segregation of their waste streams. This will allow us to properly quantify and target the specific waste streams. Existing abattoirs should consider retrofitting their plumbing, while greenfield abattoirs should potentially consider proper hydraulic planning to allow for access to these individual waste streams and to minimize cross-contamination between them. The next issue, which is probably the biggest issue, would probably be the legislative market access barrier. As mentioned before, there is no legislation or clause that prohibits the use of recycled water in meat processing, as long as the treatment process is validated and approved. Therefore, further consultation with the relevant industry stakeholders and health regulators are required. Potentially, pilot testing of the proposed potable water recycling treatment trains is recommended as a proof of concept, and also allow for technical validation of the treatment process and final product water quality monitoring. Thank you.
Great, thanks very much, Han. So at this stage, there's been no questions come through, but if anyone's got any questions for Han, please feel free to send them through. Our next presenters will be Gareth Forde and Max Barnes, and I will just share Max's screen so that you can see his presentation. Please let me know if you've got any problems seeing the presentation. It should be up now. A blue slide saying recycling opportunities. Thanks, Max.
Great, thanks for that, Amanda. So following on from what Han has been talking about, we have been working on a project for providing a portable water recycling plant to enable processors to identify the most efficient and economic water treatment options. So our objective here is to achieve the lowest cost Class A recycled water we can. And just going off the slide that Han has been talking about, we've been looking at either in-plant recycling or end-of-line recycling. So it's a very versatile, portable little bit of plant. So just as a bit of background, with the 2020 Environmental Performance Review, we found that water use intensity has reduced by 8% since 2015, which is pretty good, mainly through low volume practices and non-utility, non-production applications. So things like cropping, irrigation, yard wash, primary belly wash, those kind of things. But our aim here, our primary objective is to enable a higher volume of recycled water to a better than potable standard for utility application. So things like boiler makeup water, cooling towers, hand washing water, sterilization water, final belly wash, things where we can really return an economic benefit as well as a sustainability benefit. So just a little block flow diagram at the bottom there. So we're targeting the lowest salinity water we can, going through a primary cooling system. First, it will hit a microfiltration and an ultrafiltration membrane just to take out whatever grit or larger suspended solids we can, and then a reverse osmosis unit to hit those smaller dissolved solids, and then delivering Class A water to utilities. So Gareth will talk a little bit now about the sources of recycled water we've been looking at so far within the plant. So I'll hand it over to Gareth.
Thanks, Max, and thanks, Amanda and Madden, for the chance to talk today on a pretty exciting area of water recycling. And Han gave some really great background information, motivation there for increasing potable water, and even those increasing trade waste costs, and for red meat processors that are paying invoices to water utilities. It's quite often associated with the volume of the water and also the composition of the water. So the one that we're really hitting here is that volumetric charge on trade waste, in addition to reducing the volume of potable water required. When you have a look at all of the water streams going around a red meat processing site, quite often there's almost a binary approach of that potable influent and then the used effluent. But if you look at the water use as more of a continuum in terms of the very, very high quality water, so that might be the reverse osmosis water that's currently going into the boiler makeup or the cooling tower, through to your potables, and then you might have bore water with a high TDS, and then into things like reuse water, belt press wash water, cattle wash water. And then you start to move into your effluents. And when you look within these effluent streams, you'll find some of them are actually very, very clean. So a used sterilizer water stream may have better quality water than bore water or some other of the water streams available. So the premise of this project is what low-cost physical processing options, such as membrane filtration, ultrafiltration, are available to take these forms of water up into these higher uses, with the number one aim being offsetting utility water. So we're not chasing the production water or water used within the production area. And just as a bit of a guide here on total dissolved solids, so that really high quality RO may be down around 10 parts per million TDS, 10 milligrams per litre. When you move up into potable water, that'll routinely be sort of mid 200s through to low 300s. When you start looking at surface water, bore water, you know, that can be up towards 900. When you start looking then at these used water streams, some of them may have quite low total dissolved solids and low contamination, and hence would be a really good feed for that simple physical processing step to then be able to recycle it back up into your process. And then obviously these much higher total dissolved solids contaminated streams not being the best for those internal recycling opportunities where you're only using the physical separation, unlike where Han mentioned taking on that bioreactor approach, which is not the premise of our project. So moving on to the next slide now, you'll see a flow diagram for a plant. We'll just moving on to the next slide. I'm just waiting for it to update at my end as well. This is a high level block flow diagram for a plant. And just to provide some indicative numbers here, the sterilisation water flow rate has been taken back to 1 as an index to 1, just to give you a sense of the size of flows going through the rest of the plant. Viscera table water at say 14% that of the sterilisation water are the main two streams that we're really looking at. There are some others which may be in there, such as cabinet wash water or other lower salinity water flows that are not heavily contaminated. So that gives you an equivalent index of 1.14 of low salinity water, which only needs physical filtration to be taken up into higher quality water, such as those used throughout various utilities. So we have a look at different streams on the utility side: cattle wash water and other hard surface washdown water, biofilter makeup water, cold reuse water, evaporative towers. This is quite an interesting one when you look at some of the innovative technologies coming through around dry cooling or adiabatic coolers, which are dry coolers with wetted pads for those times when the dry bulb temperature doesn't give you the cooling you need. There's a pretty exciting opportunity for red meat processors to dramatically reduce the volume of water used in evap towers. So hence, the one that we're really chasing within this is the boiler makeup water. A couple of reasons for that. One of the reasons being the elevated temperature of that sterilisation water being better suited to the higher temperature boiler makeup water. So at the moment, total utility demand for a particular site with those evap towers, 1.41. So as you can see, that utility water is larger than the recycled water. So you've got two options there. You can really target those utility streams that you want to. So for example, the boiler makeup water, or you can potentially mix this water with, say, tertiary treated water or advanced treated water to get the volumes that you're after. And as you can see there, there's an opportunity towards 20 odd% of potable water to be replaced with recycled water. Moving on to the next slide, we'll talk through those main technologies to be included as part of the pilot. Microfiltration, ultrafiltration. So this is effectively the first step before reverse osmosis. It is a sterilising process due to the ability to physically remove those microbes. You do have quite high recovery of the water. You do need some water for regenerating or cleaning those filters. One of the challenges within red meat processing is the build-up of those fats, oils, greases, hair, other particulates. So you have backflushing, chemical treatment, and then you, as part of this pilot, looking at things like wire strainers, basket strainers to prevent clogging of these membrane systems. What's the punchline on this? You're looking at about 50 cents total cost of ownership. So that includes CapEx and OpEx over the life of plant per kilolitre produced. So you can see why at these reasonably low total cost of production of water, why it's a very high interest to start to reduce the potable water usage. Then if you move on to the next slide, so after you've done that microfiltration, ultrafiltration, looking at reverse osmosis. Reverse osmosis was not going to be included initially in this project, but the feedback that we had was the difficulty in segregation, and picking up on one of Hans' points in terms of a great opportunity there is around those plumbing retrofits, segregation of waste, and thinking more of that continuum of water quality rather than just inlet or outlet. So from that feedback, sites said, look, it's pretty hard to get segregation of sterilisation water, so hence RO is considered for that end of pipe recycling. So as mentioned, that tertiary treated, advanced treated water may be up around 1,000 to 2,000 ppm. So you've really got to desalinate that water for it to be useful within utilities, so hence the need for RO. The negative things about RO, you do need a lot of regeneration water, so you may only get towards 50% recovery. And when you look at the total cost of ownership due to that higher CapEx for outlaying the RO modules, and then the OpEx, pumping, more chemical cleaning, comes out about $1.50 per kilolitre over the life of plant. So as you can see, if your potable water plus volumetric charges are higher than this number, then it's certainly worth pursuing. So that gives the technical background on the project. I'll hand back to Max now to give some more details on the actual pilot.
As I mentioned, the current pilot project we're running right now is a 20-foot containerized micro and ultrafiltration with a RO system, along with 2 by 25 kilolitre buffer tanks. So the plan is to provide 3 pilot plants to be shared between 9 plants, with 9 months at each site. So that's including delivery, installation, commissioning, training, operation, demo, refurbishment, and removal, but with an actual operating time of around 1 week per stream of interest, however many you may have identified at your site. So an expression of interest has been sent around already. If you have not received this and are interested in participating, just get in touch with me and I'll send it over to you and we can have a chat about what available waste streams you might have. So some suitable streams to help identify if this would be something that you could host at your site would be things like sterilizer water. At the few sites we've been to so far, this has been the main one we've identified. Sterilizer hand wash water, if it might be mixed together. Viscera table water, bore water has been surprisingly attractive. Wash cabinet, tertiary wastewater treatment plant effluent, so things coming, say, out of a DAF, ideally without chlorine dosing, or any sort of recycled water that's currently stored on site. So essentially what we're searching for is just the lowest dissolved and suspended solids, and the lowest fats, oils, and grease, and the lowest microbe content. So basically what that would look like is the least cloudiest recycled water you might have on site, basically. Ideally up to about 100 meters cubed per day to feed to that pilot, which would produce approximately 50 meters cubed of actual recycled water. So I'll send it back to Gareth to talk about the process flow diagram we've developed and some of what that sort of system architecture would actually look like on your site, and then I'll talk a little bit more about some of those more detailed requirements for participating.
Thanks, Max. I won't dwell on this too long, but it just gives you a bit of a sense of the opportunity. Sterilisation water is too hot for sending into polymer membranes. The target temperature is 35, so we'll have a pre-cooling and product reheating heat exchanger. So that helps to recover the heat of the system back into, for example, the thermal well or the boiler header tank. Then another trimmer heat exchanger and a final dry cooler to take the temperature off, a buffer tank in there to ensure there's enough volume and to steadily work through the water as it's available. As we look through the process, microfiltration, ultrafiltration, so about 80% of that filtered water going into the breaker tank, 20% used for flushing and cleaning. Then that filtered water going into the reverse osmosis system. And when you look at the total, about 50% by volume of that water will go to the existing wastewater treatment plant, and 50% can then be reheated via the heat exchangers and sent over to the boiler header tank. You need power for the dry cooler skid, power for the containerized system itself in the tens of kilowatts, not the hundreds. There'll be some comms there for temperature conductivity. And as Max mentioned, some breaker tanks there. One of the advantages of cooling will be the coagulation of fat. So by having a higher volumetric flow of water than what's required for the container, we're able to get a float off of coagulated fogs there as well to help bring that fog down. And there'll probably be some Y strainer and basket strainers within here for the removal of hair, fats and other particulates. One of the big questions has been, what impact will this have on the overall salinity of water leaving the plant? So running some quick numbers for the pilot, that's using about 50 cubic meters per day back into the plant, producing, say, 117 total dissolved solids, which is better than potable. That would increase salinity by about 1.24%. If you put in a commercially sized system targeting 20% recycled water back into the facility's utility water with the same TDS level in that recycled water, the TDS and the outfall would increase from about 1,678 to 2,068. So that's a 23.3% increase in TDS with that lower new outfall. So these numbers need to be kept in mind. If the facility is really butting up against allowable TDS levels, be it for agricultural purposes, cropping, or the outfall requirements on your trade waste, this would need to be considered as to whether that would take you over any threshold, or whether further shandying of this higher salinity water may be required with other streams of water, such as bore water for irrigation, if you were to want to do this at the commercial scale. So this is one thing we'll keep a pretty close eye on through the pilot, will be the impact on the overall salinity of the total site-wide outfall. Okay, back to you, Max.
Yep, so this is just a couple of pictures to give an idea of what the scale would look like. So in the top left here is just a little mock-up we've done showing the relative scales of the two tanks in the 20-foot container. So there's no, thankfully there's no hazardous areas or anything like this, so you can keep it fairly tight. So we wouldn't expect the surface area of this to exceed anywhere between, say, 80 to 100 meters square. The top right image here is just a couple of images of the skid-mounted micro ultrafiltration membranes. And then on the bottom left there is just a little photo of a operating containerized reverse osmosis unit. So as I mentioned, for the expression of interest, if you're interested, just get in touch with me. There's my email there. So what we'll be asking from you in order to assess your viability for hosting this, just any sort of water recycling sustainability targets you might have from from within your plant, any sort of past projects or feasibility studies or anything like that you've done on water recycling, basically how familiar you are with water recycling, available hydraulic diagrams, process flow diagrams, that kind of thing of your wastewater treatment plant will basically just help us to plan out and be more efficient with sampling and where we fit this in. The commitments from you would be being able to allocate personnel resources of about 20 minutes a day for visual inspection and inlet-outlet metering. We will have some online metering, but there might be a little bit extra we might need to ask of you. Suitable space for the container and the 2 by 25 meter cube tanks. So as I mentioned, not expected to exceed 100 meters square. Available power in the tens of kilowatts. It's pretty low tech. Not expected to exceed 50 kilowatts. And the critical one is just having the wastewater available. So low salinity wastewater, minimum 20 up to about 100 meter cube per day would be great if you could make that available for us. So were there any questions? I can't see the chat, but
Yes.
Were there any questions?
Got some questions came through on the SMS while the presentations were going on, so I'll go through those in a minute.
Yep.
I just noted at the end of your sorry. I just noted real quick, your presentation there that the EOI process for the water recycling pilot actually is to go through the co-innovation managers first, and most members will have already done that. And so we'll be sending those applications via the co-innovation managers over to you, so you can start your process around interviews, etc. So that's where the there might be some laggards, but they should contact their co-innovation manager, and if they're interested, you're quite right. You'll get to see them after that. So thank you very much to both sets of speakers today. That it was really good the way one flowed to the other. We've had a couple of questions come through on the SMS, so I'll just go to the first one. The first question is around the MBR that Han talked about. Han mentioned that the MBR needed to have a DAF pre-treatment. Could the MBR unit be replicated with a more economic alternative to achieve Class A?
I don't think there would be. I don't think there would be at this point in time, just because you need to achieve the microbial removal, depending on. So as in, like, I don't think you'll be able to achieve that without using an MBR, because the MBR would not only remove your nutrients as well, and it will also remove the microbes. Just using a membrane alone would probably only do the microbial aspect, but not actually do the nutrient aspect. So it still has to come back to a nutrient removal process, which the current state of the art would be a biological process. And within the biological processes, you are limited to either activated sludge or an MBR in this case. So.
Thanks for that, Han. Moving on to another question. The time frame was mentioned in the pilot that the container would be on site for 9 months. Can you please explain what happens during that period of time? So I think Max or Gareth, if you could mention that a fair bit of that time is made up through design, delivery, installation, and then again at the end via demobilisation, cleaning, reconditioning, etc. So the actual operating time is a bit shorter than that, is that right?
Yes, that's,
I think it's
you
about 2
basically
months,
just said it there, mate.
Yeah.
Yeah, you basically said it there. Yeah, so most of that time will just be for working out, you know, exactly what streams are going to go into the system. So working out any sort of piping and pumping requirements, which will all be sent around. And then, yeah, the sort of delivery installation will take a few weeks each time. Commissioning, training, another couple of weeks. Operation will be a few months, but actually you'd probably only need about 1 week per stream to actually just, because this is a pilot project, so it's just basically demonstrating that it works. And then the demob, refurbishment, removal would be the other side of that, the remainder of that 9 months.
Thanks for explaining that, Max. That's good. Another question on the recycling pilot. There was emphasis on the kill floor as the main source of water for treatment. What about boning room as an opportunity for Class A to be used as bottle makeup? So either Max or Gareth?
Yeah, Gareth, you want to take that one? I'll get up your
Yeah, great. Thanks for the question. Yeah, quite interesting. So in terms of kill floor, the kill floor sterilisation water, anecdotally has had more hair, more fats in it, whereas the boning room has been a little bit cleaner. The main challenge with making those sweeping statements is the ability to aggregate those segregated streams to be able to sample and define that categorically. So most sites will tend to start to aggregate it together, and you really just can't get into that. The sites that we have looked at, if you can segregate that boning floor sterilisation water and hand wash water away from the kill floor, that will tend to be higher quality. So maybe 200 to 300 ppm, as opposed to once you aggregate kill floor and boning room and some other of waste streams, it'll tend to get up towards that 500 ppm total dissolved solids. So yes, it would appear anecdotally boning room water is better than the kill floor or the site-wide aggregated sterilisation water. And so what does that all mean? It's a really good question. You tend to have a compounding advantages when you have that low salinity water being sent back to utilities that require that low salinity. So what do I mean by that? Having a look at boiler makeup water, if you can reduce the salinity of boiler makeup water from 260 parts per million, which is a pretty common salinity for potable water in Southeast Queensland, to 50 parts per million, then that can result in 76% less water being required, because you have that much bigger diluting effect of that desalinated water. And so even when you take into account the washed and recycled water needed for generating that RO water, you're still ahead. And especially where you can use that higher salinity water for things like wash down water, counter wash water, belt press water, then that's a great opportunity. So yes, if you can segregate the stream, boning sterilisation water does appear to be better than the kill floor sterilisation water. If they're being aggregated together, that does certainly has been shown to be better quality water than either a general recycled water, or probably has some advantages over end of pipe recycled water or tertiary treated water as well. So yeah, good question. It is the premise of the pilot, is to see which sites can access or segregate which streams, and then what is the result when those streams are sent through the filtration and RO processes.
Thanks, Gareth. for clarifying that. And the other thing with the pilot is that we're looking for different opportunities that members can suggest in their EOI as to what source of water they would like to have as a candidate, or several sources of water that might be. Another question is to Han. Han, there was a really low water usage site. What were they doing differently? And I think I know that site. I can't say who it is, but I think it was very low water intensity, down to about 2 kilolitres per tonne of hot standard carcass weight. So in your plant interviews, do you remember what they were doing differently?
I think that was most probably because they were already having a lot of on-site water treatment processes, and depending on, again, I think some of them are already recycling some of the water, but not for potable reuse. So mostly in their stockyards, mostly a stockyard wash down water. That's what they do. But across all the processes, they all have varying levels of on-site treatment. Some are pretty extensive because they're producing biogas, and so I think that answers the other question of whether anaerobic digestion can be used for nutrient removal. It can, and it's widely used, but it's not used primarily for nutrient removal. It's more for biogas generation, and in the same process, it also has some nutrient removal capability. And that's probably a reason I think processor 3 has that on site, and probably is the reason why they use less potable water compared to the rest.
Yeah, that's right. Yeah, thanks for that, Han. That was that plant in particular had considered every source of water, what they could do with it, and then every after treatment, where it could be used. So thank you. We've run out of questions. I think, Amanda, we don't have any more questions here, and we're just about out of time. So I'd like to thank Han and Max and Gareth again for their great presentations. Back to you, Amanda.
Thanks, Matt, and thanks to Han, Gareth and Max for a really good presentation. We've actually had quite a few people also ask whether they can get a copy of the presentation. So what we'll do is we'll send through a copy of the presentations as well as a recording of this, and hopefully we'll be able to get that out to you by tomorrow. So thanks everyone, and if you've got any further questions around the webinar, feel free to reach out to either Matt Deegan, the presenters, or your co-innovation managers as per the relevant states. So thanks very much and enjoy your afternoon.
Thank you.
Thanks everyone. Bye.
See you guys.